Hello everybody, and welcome to another lecture of 6837. It's getting suspiciously close to midnight, so I better get started with our recording for the day. I'm going to fall behind schedule. Today, we're going to talk about one of the really fun advanced topics in computer graphics that we only get to summarize in 6837. Sadly, your homeworks are not going to cover this particular topic, although it is a popular topic to study in the final project. In particular, the topic is global illumination. So we're going to start by discussing the global illumination problem and some of the existing strategies for tackling global illumination in the ray tracing pipeline. And then we're going to step back 10 feet and talk about Monte-Carlo integration, which appears here and in many other places inside of ray tracing and rendering more generally. So to get started, we're going to ask a pretty simple question, which is, does ray tracing actually simulate physics? Now, for any number of reasons, the answer to this question is very clearly no, right? For probably the most obvious reason is that photons start at the light bulb and go into your eye. Yeah, but during the ray tracing algorithm, we do the opposite of that. We send a ray from our eye back to the light bulb. And so the terminology for this, although textbooks do disagree, but the typical terminology for the strategy that we've covered in ray tracing might really be called backward ray tracing. We're tracing rays of light backward from our eye into the light source. Now, why is that? Well, let's say that we just take a random photon that is scattered outside of this point light, for example, what's shown on this slide here. Well, this is a point light, so it sends an equal amount of light everywhere. So I randomly draw a direction, there's one, and the photon just zips off the slide. Was that a very useful photon when it came to rendering? Well, no. I mean, what I can render are exactly the photons that go through this little screen door and into my eye. And so the basic motivation behind the backward ray tracing technique is that we only really care about rays that actually reach our eye, and this is one strategy for finding them. At the same time, it's not really simulating physics, and indeed there are a lot of phenomena that you can't really capture using this particular technique, which is just leveraging the fact that physics is very symmetric. So the reality is that ray tracing is full of tricks and approximations, and many of them are really intended to cope with the fact that we're doing backward rather than forward ray tracing. So for example, when we talked about transparent objects, really our transparent objects in this class, so far at least, really can't cast a shadow because shadows are quite complicated for transparency things, or you can't have a lens that takes light and focuses at a point. Anything where the light takes a nonlinear path to its destination in a way that's hard to trace in the backward direction. And so this really prevents us from being able to render phenomena like caustics, which are caused by light focusing and being redirected in all kinds of crazy ways within a scene. There are also more subtle rendering effects that we also are unable to simulate. So for example, one thing that we've completely disregarded, if you recall that Cornell box example that we've talked about before, let's say that we have a red wall and a white floor, and then just some light source. Well, if we render this scene, when we look at the white floor right close to the edge between the red wall and the white floor will actually look a little bit red. That's because there are some rays of light that are hitting the red wall. Sure, they're getting scattered every which way, but and in the process of being scattered, probably losing a lot of energy, but a tiny amount of that energy hits the white and then maybe goes back to your eye. So far, that effect has been pretty much disregarded. It's not a caustic, but it's some other secondary lighting effect. And that's another one that we're going to talk about today. So using advanced techniques, we can capture all kinds of cool images. So for example, here, by using photon mapping, we're able to see the refraction effect going on underneath this transparent object. So what's going on here? Well, we have a cube. Now your instructor is going to fail at drawing a cube despite being a geometry professor. We have a light like this and the ground underneath, and the light is going through the cube doing its refraction thing. So the path of light is actually changing as it goes through this object, and then maybe focusing on a particular region underneath. So if you think about the backward ray tracing algorithm, it would be quite difficult to capture this particular effect, because what you'd have to figure out is exactly what points on the ground plane have some nonlinear weird path that goes backward from the ground plane back to the light, accounting for the index of refraction and so on of the piece of glass. So instead, how are we going to render this particular scene? Well, forward ray tracing is going to come to the rescue. So the idea here is that we're going to shoot a ton of photons. Notice that photons is in quotation marks, and that's not by mistake. We're not actually simulating, wave packets. But here we're going to do it with the expectation that most of them are not going to hit the eye or the camera, but rather we're just using it to get some idea of how light gets distributed when it leaves the light source. And then we're going to use that as some external information during a second pass where we actually do the rendering. And this is all to avoid a really, really hard inverse problem, which is how can I figure out where to send a photon so that it actually reaches a particular pixel or the location of your eye. So this is the problem that we want to avoid. And so our strategies for global illumination, this idea of trying to capture all the different places where the light goes, are going to be to kind of meet halfway in between. So rather than solving the inverse problem, we're going to scatter light out to different points, attach the light to those points of the scene, and then do our ray tracing just like normal, accounting for the fact that we just noticed a photon kind of coming nearby. So don't worry, we're going to fill in a lot of detail as we move forward in today's lecture. Now, one theme that we're going to have is that all of the techniques we'll talk today are going to make use of a ton of randomness. We're going to see that we're just scattering photons every which way. And the more that we send out and more random directions, the better our scene gets. This is going to be the main expense of our global illumination and ray tracing algorithms, but also the source of the power here. That by approaching rendering in this fashion, we can get some really nice results at the cost of spending a lot of computation time. So anyway, at the end of lecture, we're going to broaden and talk about how we can improve these randomized strategies to converge faster and give us better images with lower amounts of noise. So here's our outline for today. We're going to talk about the global illumination problem. That is the problem of simulating all the different photons as they bounce around the scene. In particular, we're going to introduce the rendering equation, which is actually an equation that you're attempting to solve when you render a scene. Believe it or not, you probably don't think of rendering as solving a system of equations, but that's actually what you're doing. We're going to talk about path tracing and some of the other algorithms out there for solving global illumination in practice. And then in the last part of our lecture, we'll talk about more general strategies like importance sampling, stratification, and so on, which are intended to get a better distribution of these randomly scattered photons in order to reduce the amount of noise, right? So what we'll see is that initially our global illumination techniques will look something like the top here. So there are caustics. This is a global illumination algorithm, but this is probably very noisy relative to what you would actually want. And then we're going to see that by employing some of these strategies, we can use the same amount of computational power, but get a much nicer image. Okay, so let's talk about the global illumination problem. So far in our ray tracers, we've only seen direct lighting, which is the red ray here. So the red ray of light, notice that we're doing backward ray tracing, so it's going from the eye back to the light source. The red ray of light hits the wall and then goes directly to my eye. There's nothing too crazy here. But we also might want indirect lighting, which is to say that the total amount of light that hits this point is actually, and I'm sorry to say it, I know there's a little bit of calculus here, it's actually an integral. That is to say that I need to draw a little sphere, or maybe a half sphere because I'm on the wall, around this point, look at every possible incoming direction, and account for all the different light that's coming in, scaled by the BRDF. And we'll see that that actually is going to make some more sense. I mean, if you think of a BRDF as the fraction of incoming light that gets reflected out, then really when we render, we should be doing a double integral. Whereas in our previous lectures, we kind of somehow got away with a finite number of calculations, like just a few rays. So in practice, we're just going to send we're going to send hell of rays into our 3D scene here, essentially to account for that spherical integral. And they're not all going to be ones that are determined by some physical law, like the law of reflection. We're also just going to scatter them out every which way. Now, why bother doing that? Well, here's the kind of thing that it can do. So here's our favorite example again. Remember that this is sometimes called the Cornell box. You can guess where it was invented. So the Cornell box contains a few different objects. I always get it wrong. I believe this is a reflective sphere, and this is a refractive sphere. And both of them are kind of annoying cases for rendering. But one thing that you might notice about this image is that it's quite dark. Yeah. So for example, the ceiling here doesn't receive any light from the light bulb, even though, the reality is that probably some light bounces off of the sphere and hits the ceiling and so on. So today we're going to add different effects, and it's going to take our Cornell box from this kind of dark criminal scene to something a lot brighter. So let's toggle back and forth. There's a darker one with all my writing on it, and the brighter scene. And there's a lot of different effects here. There's caustics. The ceiling is receiving lighting. If you look really closely at the floor here, it's red-ish. And if you look really closely at the floor over here, it's blue-ish. And all of these are the sort of secondary or indirect lighting situations that the ray tracing algorithm that we've talked about so far is unable to capture. Okay, so far we've only discussed BRDF for point lights, which is to say that the only light sources that get bounced off a surface are kind of like little delta functions that are hitting the BRDF at just one location. But the reality is that a BRDF is really more like a differential object, even though we didn't really see that when we talked about it last time. And that's because it describes how indirect illumination reflects off of a surface as well. And so rather than summing over just a finite number of light sources, kind of like a set of delta functions if you're an electrical engineer, this is the sort of simple ray tracing, that we've seen so far. We're going to move to a more complicated picture where instead of just summing over the light sources, we're going to compute an integral over the entire half sphere that accounts for all of the different places where the light might have come in, like a tiny amount of light bouncing off the floor and all that good stuff. But of course, this is computationally intractable to do in complete accuracy. Computationally intractable. I think you guys can see why I'm very afraid of teaching a math class this spring. I don't think it's going to go well. But for now, our PowerPoint slides are okay. So let's see if we can express this mathematically. In particular, one thing we can do is to derive something called the Reflectance Equation. And this is really just a souped up version of the equations that we were working with BRDFs in previous lectures. So here's what it looks like. So let's say that I'm at a particular location on a surface, or really anywhere in a 3D scene. And this is the out direction. Then the reflectance equation is trying to tell us how much light comes off of a surface based on how much light came into the surface. So let's see what that means. So in particular, what we're going to do is take an integral. This is L here. And L is ranging over all of the different points on this hemisphere, which are all the possible directions where the light might have come in, right? So let's take a look. Now we integrate the product of three things: the amount of light that came in at L, the BRDF, which is describing the attenuation of light as it bounces off of L and then leaves in direction V, and then this cosine term, which is really just accounting for the fact that the component of light that's parallel to the surface doesn't get reflected. It just kind of wings right off of it. Okay, so this all seems believable, right? Like the amount of light going out is just some integral of the light coming in scaled by the BRDF. And you might be saying, well, Justin, why is this so complicated? Like there are numerical methods out there for computing an integral. But the question you should ask is, where does L in come from here? What is that number? Well, if we step back to 10 feet and kind of squint and stare and scratch our chins for a few minutes, philosophize, what we'll realize is that L in is somebody else's L out. Yeah? And in fact, my L out might be this point's L in and vice versa. So notice that this is kind of a circular definition in a sense, right? It's saying that, well, the amount of light coming in here has to do with the amount of light coming out over there. The amount of light coming out over there has to do with the amount of light coming in here. So overall, this is starting to suggest that we actually have a system of equations to solve. It's somehow recursive. And in fact, notice that this Ln maybe has some other hemisphere somewhere else that's also affecting it. So the basic point here is that light is getting bounced every which way in a scene. Now, why is it that we don't need such a complicated algorithm for somehow solving this implicit set of relationships? Well, the reality is that this fraction is quite small. And so in other words, a few bounces of light later and it's basically gone. And so just by accounting for those direct terms, like what we've talked about already, we already get a pretty good rendering. Of course, we haven't actually accounted for that direct term yet, so let's do that. So here is the full rendering equation in all of its glory. I'll draw a little star here because this is an important equation. So what is it saying? It's saying that the amount of light that's reflected off of a surface at location x in direction v can be expressed as the sum of two terms. One of them, which we already saw on the previous slide, is basically the amount of light that bounces off of the surface after you account for all of the different incoming directions L. But then there's a second piece of the rendering equation, right? Because these x's here are there's a lot of different x's, so there's a lot of incoming light coming from different places. But there's a second term, which now we're going to add on this slide. And that is accounting for the energy of point light sources, right? So there are just some locations that produce light, maybe from electricity or whatever. And so we just need to add some other term, E out, which E out is just saying that at location X in direction V, maybe X is actually a light source, in which case this is some mysterious source of light energy in our scene. Okay, so this full thing is the rendering equation. And remember that the challenge here, the reason I keep using the word equation, is that my L out is somebody else's L in fact, many other people's L in, and their L in probably includes my L out. So what does that mean? That means that the rendering equation is actually something called an integral equation. And at that, it's actually a really complicated one, which is to say that if I want to compute this function L, which is really what I'd like, right? Somehow that's the light field or the thing that I want to render. It's on the left-hand side and the right-hand side of this integral. And this integral is coupling together every point in our scene with every other point in our scene. And so this is what makes rendering so hard to do if you really want to account for global illumination. That you have all of these different relationships that relate L to itself based on taking a bunch of integrals. And you somehow have to invert this whole system, which is linear, in order to generate L. Now, there are some algorithms out there that actually just attempt to solve the rendering equation. But for the most part, we're going to discretize and solve in a Monte-Carlo fashion, assuming that this attenuation really goes to zero after a couple bounces, which is sort of the blessing of the reason why we're able to solve this in practice in some approximate way and get a believable rendered output. If you're wondering, Typically, there is no analytic solution to the rendering equation. I actually don't know if, like, maybe in 2 dimensions somebody's worked out some really simple one, like a sphere in a box. If anybody knows, I would love to see that. But there are many ways to solve it approximately, but because of course, solving a rendering approximately is exactly rendering a scene, which is something we do all the time in computer graphics. And so today we're going to talk about Monte-Carlo techniques, which use random sampling to evaluate these integrals. One question that I sometimes get is like, well, why not try to write down some approximation of this giant linear system and just solve it? It turns out there are people to do that. So if you're curious, if you Google the term radiosity, that's roughly what they're doing. They use techniques like the finite element method to actually write down all the unknowns in the rendering equation and try to solve it like a linear system. These are some pretty crazy algorithms, and they get really complicated really fast. I actually don't know the details here, but I'd love to learn more. Okay. So now we're going to switch our attention from the theory, which hopefully you have some idea of at least why global illumination is hard. And we're going to switch to the practice. Like, how do we actually render global illumination in practice without the excruciating pain? The technique that we're going to talk about today, which is not going to be covered on your homework, but is a popular project topic in 6837, is to use Monte-Carlo ray tracing. Now, you might know that Monte-Carlo is a place where you can go gamble, and this is a common term in computer science for referring to randomized algorithms that essentially scatter data collection all over the place and then use that to compute averages and integrals. So here's going to be the basic outline of the Monte-Carlo ray tracing algorithm that we could use here. And this is a really simple one for global illumination. So remember that our goal here is to solve the rendering equation. In particular, we don't need to solve it everywhere. Really, all we need to figure out is that we draw a ray from our eye into the scene, and we find the first place that it runs into. Let's call that place X. Then really, if I draw a vector back toward my eye, X, oh, oops, I already used X. Let's call that V. Going back to our definition here of the rendering equation, notice that the color that should appear at this pixel is exactly L out of X comma V. So this is actually the value that we render. This is the information that we need at the end of the day to render this one pixel. So what are we going to do? Well, remember the rendering equation here basically says, well, if we want L out V, one way to compute it is to compute this integral on the right. So what we're going to do is we're going to randomly sample a bunch of directions L, and then we're going to, well, try to compute L in that direction. But of course, things are going to get complicated fast because Ln also needs an integral just like the one that we've shown here. Okay, so the question is, how are we going to basically stop that process from infinitely recursing? And here's what this looks like. So we cast random rays from our hit point to evaluate that hemispherical integral that we saw in the rendering equation. And now, of course, we've bounced these things off to other points, and we can recurse, right? And so now I have some new hemispherical integral that I need to compute, and we can keep going. But the thing about the rendering equation is that this procedure is never going to stop. So what do we do? Well, as with many tricks in ray tracing, what we're going to do is just add a recursion limit that says, if I recurse more than, say, 5 times, or probably more like 2 times, I'm just going to assume that the contribution is 0. Now, if you're following, you might say, well, wait a second. So I recurse a bunch of times, I return 0, and then I undo all those steps. Then what am I going to get for my color here? Well, I'm going to get 0, and that doesn't feel right. And essentially, what I haven't accounted for is the light source. So here's going to be the trick, is that rather than just purely computing that hemispherical integral in every step of global illumination, I'm going to do 2 terms in that integral. I'm going to add a term that systematically accounts for that light source. Remember, that's that special energy term in the rendering equation. And I'm going to add that to the hemispherical integral, which is usually much smaller. And so essentially the idea here is that we can't wait until the rays just hit the light source by chance, because as we've already seen, the likelihood of that is basically 0. Okay, so hopefully this algorithm makes sense. So we figured out that we want L out at this particular pixel or location in the world by tracing a ray out from our eye. Now we draw a hemisphere around this point to draw secondary rays, just using a Monte-Carlo integral. And the idea here is that we're just sampling the L in these different directions that we're going to attenuate by the BRDF and add to the light that our eye receives. But every time that we recurse, in addition to doing that hemisphere, we're also going to account for the light that comes directly from the light source. In fact, that's the dominant term. Everything else is secondary. So what is the result? Well, we get a pretty nice looking image. This is already our scene here. Now, this was a substantial amount of computation, but you can see that, well, the image is really noisy, right? Especially in areas where this global illumination effect is really the only effect that's bringing light. Now, why is that? Well, at every point, we're computing this fancy integral, and the way that we're doing it is just randomly drawing a few points on a hemisphere, evaluating the function at those points, and adding them together. And yeah, that's some approximation of a spherical integral, right? It's the Monte-Carlo one that we're going to talk about at the end of lecture, even more detail. But the more samples that we add to that integral, the better it gets. So if we only have 10 or 100 samples on the hemisphere, that's not very many. And because they're randomly drawn, that's why we see all this noise. But it feels promising. Like, notice that there's a blue tinge on the side of the sphere and a red tinge on the side of that one, which is pretty cool. So like, if I saw this and I were a researcher back in the 80s and 90s, I'd get really excited because I somehow have taken the first step toward global illumination. So what are we to do? We have an image that we like, at least from a macro scale, but all the pixels look really noisy. Well, we could increase the number of samples, but pretty soon we're going to be out of the regime of a reasonable amount of computation. Our rendering is just going to take forever, and that's no good. So essentially, you can think of almost all of the rest of our discussion today on global illumination as different techniques for making this procedure more efficient. So one of those, something called Monte-Carlo path tracing. Notice that our previous algorithm was Monte-Carlo Ray Tracing, is going to do kind of a sneaky thing. Now, in general, we can always approximate an integral in a really, really crappy way. And that's really what Monte-Carlo path tracing does. It says, so let's think in one variable for a minute. Let's say that I want to compute the integral of a function. So I have the integral from a to b of f of t. dt. It's an undergrad class, so I don't want to forget my dt. Now, there are a lot of different algorithms, right? I could sample a bunch of t values, compute the average value of f of t on those t values, and then multiply it by b minus a, right? So that would be sort of the simplest thing to do, would be to draw a bunch of random t's from the interval between a and b. This is like throwing darts, right? So I have, here's a, here's b. Just draw a bunch of t's. And now I can take their values and add them all together. And divide by n. So this is the average of our samples between a and b of our function f. Well, if I multiply that by b minus a, then I get some approximation of the integral. This is what we're going to call the Monte-Carlo integral, right? So this is, this expression here is approximately equal to the integral from a to b of f of t dt. And now as we take this number n and we make it bigger, our integral gets better. So in the path tracing algorithm, now for one thing, the integrals that we care about in rendering and ray tracing are not over the unit interval or the interval from A to B, they're over a hemisphere. But the same principle applies. You randomly draw some points on the hemisphere and average their values together. Now you scale by the surface area. Here's a trick that we're going to use in Monte-Carlo path tracing. Now we find the point in the scene where the ray from our eye intersects the scene. And remember that what we really need to compute at the end of the day is this hemispherical integral. We're going to use a bunch of samples to essentially anti-alias the pixel itself. So there's a pixel sitting in front of our eye, and we're going to send a bunch of samples through that pixel. But now each one of those, rather than computing a bunch of samples for this hemispherical integral, we're going to compute an extremely noisy integral by taking only one sample. So every single time we send a ray out, and it just kind of ping-pongs about the scene, just like the algorithm that we talked about before, but now instead of there being a bunch of yellow lines out of a point, there's only one. Now, this is a really bad approximation of our rendered function here, but it is an unbiased one. It's a randomized one that averages out to the proper value. So what are we going to do? We're just going to keep sending rays from our eye into the scene. Every time we do it, the Monte-Carlo algorithm will choose a different random ping pong about the image, and that's how we're going to get our final ray trace thing. So rather than like recursing 100 times every time we have a bounce of a ray, we're only going to recurse once. This technique is called path tracing, and it's actually a fairly efficient way relative to Monte-Carlo ray tracing for drawing the scene. And again, we have to make sure that we deal with shadow rays and illumination directly from the light in every single bounce. And the basic point here is that this path tracing algorithm works okay because you really don't need that many bounces before the light that actually reaches the original source point is pretty much negligible. That really only 1 or 2 bounces in a typical scene really matter here. So what do? We just shoot one path from the eye at a time, and now we don't even really have to recurse. We can just do it with a for loop. And we're just basically, rather than randomly sampling to compute a Monte-Carlo integral over a hemisphere, we're randomly sampling the space of light paths between the light source and the camera. So hopefully that makes sense, that Monte-Carlo ray tracing might take a bunch of samples to compute the hemispherical integral. Monte-Carlo path tracing does a really bad job of approximating that integral using one sample, but it repeats computing that integral many times by sending out many different rays. And every time it does it, the randomly chosen path is a different one. And that's where it's getting its averaging out and smoothing things. So here is a piece of pseudocode for what that looks like. So now we have a function that we're calling trace path, which takes an array, and notice that now we need to remember the depth. So if the depth is bigger than the max depth, then we just say, oh, okay, well, then we're done. We're just going to return black. Otherwise, we do our typical ray tracing, right? We figure out the first thing that we run into. And again, if our ray doesn't hit anything, we return black. And otherwise, we hit an object, so now we need to evaluate the BRDF. So we get the material, emittance, all that good stuff. We generate a new ray, and the origin of that ray is exactly where we hit the previous object, and the direction of the ray is just random. It's ping-ponging off of the surface you just hit anywhere in that hemisphere. Now, we're going to need a constant value here, which is the probability of this ray. In this case, we're choosing it uniformly, in which case all probabilities are the same. Otherwise, we're going to have to account for that if we bias our distribution. And remember that our rendering equation is the product of a few things, right? There's a cosine term, a BRDF term, and the amount of incoming light. And how do we get that? Well, it's a recursive call, so we call trace path. And now, what are we going to do to figure out the color that we return? Well, here is the rendering equation. So this is that one sample approximation. Essentially, this P here is accounting for the surface area of the hemisphere, and this is our one sample, plus the emittance, which is just the light that's coming out of the surface that we're currently rendering. So notice that we only launched one secondary ray in this algorithm. This is different from Monte-Carlo ray tracing. But now, if we want to know why we don't just get a super, super noisy image, what do? Well, we loop over all the pixels in the scene. And for each pixel, we call trace path many times and average the result. And since trace path is extremely randomized, that is where we're going to get our final random color. So here's what this looks like. So here we send 10 paths per pixel, and already we get a kind of reasonable image. But now, what did I do? Well, we started with 2 diffuse spheres. And instead, I made them reflective, and not just reflective, but so there's one reflective sphere and also one refractive sphere, and suddenly our image looks even more noisy. Now, why is that? Let's think for a minute. So, let's say that I'm rendering a particular path. Well, there's some probability if I'm like sitting in this region up here, in the ceiling, let's say that I want to render some pixel here, and maybe I only have paths of length 2 or 3. So what do I do in my path tracing algorithm? Well, I draw some hemisphere and I randomly draw a direction for my ray to bounce off. So in this case, maybe the ray hits the wall, I collect the red, and now I've hit my recursion limit and I stop. And I say, okay, I get the tiniest amount of red that I'm going to add to the ceiling here in addition to direct illumination term. But now, maybe I have maybe there's one more recursive limit. I hit the white floor, but whatever, we got this negligible term and that's fine. But now maybe I render this pixel again, and now I get a slightly different random sample that hits the reflective sphere and goes in the light bulb. Well, now, suddenly, the amount of light energy that's coming back to this pixel is much, much higher. And so the basic idea here is that the variance of our integrand, like the craziness of the function we're trying to integrate, got a lot higher thanks to these annoying reflective objects here, which are essentially, in some sense, just creating another light source down here that you may or may not see, depending on whether you happen to choose a ray that bounced off and hit the area light. So what do you have to do for this glossy scene? Well, add more paths. So here we do 100 paths per pixel, and you can see that this noise, these little speckles that you were seeing before, are starting to go away. So that's the basic trick here, is just use more paths, but you can still see that this is a pretty noisy result. I don't think you could include this in a feature film. In fact, if you animated it, then of course it'll look like white noise, right? Every single frame will have a different noise pattern, which isn't great. Okay. So a few details that we've already discussed, just so that you can see what it looks like. So here's with and without importance sampling on the light. So if you don't do explicit light sampling during each one of your recursive bounces, then you end up with some pixels that are just black, which is not so great. But if you have the light sampling, then you have a slightly better scene. Now, this is with far too few samples on both sides, but it's just to illustrate a point, right? 4 paths per pixel is hardly the gold standard in path tracing these kind of complicated scenes. Now, there's all kinds of details that you probably don't think matter a whole lot, but probably do when you implement algorithms like path tracing. So one of my favorites is, how do you actually generate your random numbers? Now, I'm sure there are people in our EECS department here at MIT that have much more expertise than I do in random number generating. But the basic point of random number generation is that a computer can't really do it, usually, unless it has some specialized equipment, right? That computers are deterministic objects. They're not good at generating random stuff. And so really the algorithms for generating random numbers are generating something called a pseudo-random number, which is just some pattern that bounces around a lot. So what happens if we mess up our random number generator? Well, Then all of a sudden, different pixels are getting correlated samples in the integrals that they compute, and it can create some really crazy results in the rendered results. So, for example, here's one where we use a fixed random sequence. Like we say, oh, maybe our random number generator is too complicated. So instead, I'm going to make an array of 1,000 random numbers that I pre-compute, and then I'm just going to keep looping over and over and over again. And you can see that that creates some unintended structure in the error that actually leads to visible patterns in the rendered image. And so all of this is to say that the randomness in your rendering technique is really, really critical. And you really rely on it in every single step of this integration technique. Now, I've included a link in the slides where you guys can play with a simple path tracer that actually, kind of amazingly, I don't know who Evan is, but I'm very impressed that madebyevan.com has a path tracer that can run in your web browser. And the kind of cool thing that it does is it just keeps making the image better and better by sending more and more arrays the longer you let it sit there. So I strongly encourage you all to go to this webpage and play with it, because I think it gives you a feel for how these techniques work. Now here I show one of the original path traced images by Kaguya, one of the people who invented the rendering equation. And actually this is a great cautionary tale. So this is a very famous rendered image and one of the early convincing examples of this style of machinery. I'm sure it took about 1 billion years to generate this because it was back in like 1986. And in 1999, a graphics researcher, Bruce Walter, was trying to reproduce some of the vintage path traced and ray traced images for like kind of a historical project. He actually got the original code from Kaguya and found that his own rendered result didn't match. And it turned out that the original code for path tracing actually had a bug in it. One of the really interesting challenges in global illumination and some of these other related areas is that they're really subtle effects. And even if you get them wrong, you may not see it. So one of the things that I think is really important when you're debugging code in this area is to think about how you can design clever test cases that reveal that each of the features you've engineered independently is operating pretty well before you glue them all together. Now, path tracing relative to this Monte-Carlo ray tracing technique is still really costly. You need a ton of rays for every pixel. And the amount of computation time here just blows up. Like it can take minutes or hours to generate even a pretty simple scene. And you know, at the end of the day, we probably don't want to render the Cornell box like this. We want to render a really complicated, beautiful, realistic scene with many objects and so on. As you can imagine, the rendering time just explodes. And so a lot of effort has gone into how to simplify this procedure even further. So here's one observation that's kind of fun to think about. So here I'm showing you the Cornell box rendered to death, really with many, many samples. And one thing that I could do is take this image, just as a two-dimensional object, and subtract it from the Cornell box rendered without any global illumination at all. Let's see what that looks like. So again, this is basically the delta in pixel color between the Cornell box with and without global illumination. And so a different way of understanding this picture is that it's basically just the indirect light that's going on in the scene. Now, one thing to notice, if you look, for example, at the back wall here, is that the indirect light is extremely smooth. That there aren't like crazy sharp changes in color that go on inside of the indirect illumination in our image. That for the most part, it's a smooth function, maybe just, with the exception of the action near the sharp edges, right? So here, there's something sharp. But for the most part, it's very smooth along our image. And so what does that mean? That means that computing global illumination independently for every single pixel here is probably overkill. A different way of putting it is that if I had a sparse set of pixels in this smooth region where I knew the contribution of global illumination, I could just kind of copy it over to some other location, and that would actually work okay. And this is the motivation for many algorithms in the global illumination universe, in particular one called Irradiance Caching. Now, the basic idea of irradiance caching is to use the fact that global illumination, the effects of indirect illumination in global illumination, are smooth. And so, what does that mean? Well, it means that we're just going to sample sparsely the indirect illumination, so not at every single pixel, but just at a few pixels. And then we're just going to borrow the indirect illumination that we computed to compute it at nearby locations, right? So maybe what I do is during rendering, I just have this big for loop over all the pixels in my scene. I send a ray from my eye, and before I compute global illumination, I say, was there another hit point nearby where I already computed global illumination? And if so, maybe I just borrow the global illumination value at that point, or I average a few nearby. And so this is just a sneaky trick that says, well, in that case, I can remove that giant integral altogether and just replace it with the value that I already cached attached to some other point in the scene. So what do I have to do? Well, I have to store the indirect illumination. Remember, that's a hemispherical integral, and it's associated to a point in 3D. It is not associated to a pixel on your computer screen. And now, if I get a new hit point, I look nearby, and if it's maybe on the same object and nearby, then I'll just interpolate a few of the nearby irradiance cached values. And if I don't find one nearby, then I do a new hemispherical integral and I cache it, meaning I store it so that future pixels can use it. However, a typical thing to do is still to do the full calculation for the direct lighting. This is only for the indirect effect because that's the part that looks smooth. So here's what this looks like in the irradiance caching algorithm. So one thing that you can do is develop some heuristics that try to essentially concentrate irradiance samples near sharp features. But essentially here, the rendering algorithm is just going row by row on your pixels. And when I render a given pixel, it just looks nearby. And if there's an irradiance cache value already there, then I just use it. And otherwise, I compute something new. Now, one detail is that you probably want to shuffle the order of the pixels where you do your rendering, or else you'll get a very regular pattern for the irradiance cache, which might not be so good. But if we zoom in super close to the rendered image, let's see if I can manage to do this in PowerPoint. It's kind of a challenge. It only zooms when I don't want it to. Aha. Well, taking a close look, for example, in the upper region here, if you look, the image actually looks a little splotchy in the background. And if you think about the irradiance caching algorithm, that actually makes some sense, right? Essentially what's going on here is that each of those splotches corresponds to a single irradiance cache point, and its influence is kind of decaying nearby. So that's the basic trick of irradiance caching, which is to say, if I already did the indirect illumination for some nearby pixel, just reuse it, and otherwise compute it and then just attach that information to that point in the scene for future use as I continue my rendering. As long as I shuffle my pixels, do some other stuff, this is a really pretty reasonable technique and a very easy one to implement, right? All you're doing is keeping a long list of points. There's another algorithmic question that we're not going to answer in this course in any detail, which is, can you come up with a fast algorithm for figuring out if there's a nearby point in your irradiance cache? Remember that we discussed KD trees earlier in 6837. I would encourage you to revisit that for this particular problem. So if you like this kind of thing, it's actually been around for a very long time. So this was invented by Greg Ward, the same person who I think found the bug in Gajia's rendering. And you can actually download one of the original irradiance caching implementations in some software called Radiance, which is amazingly, I just checked today, still available online. This is a very legacy piece of software. But also this technique is incorporated in almost any major rendering system now. Now, there are a lot of different global illumination algorithms, and this is just one of many, right? So the irradiance caching algorithm is kind of pixel aware, right? I'm sending rays out from my eye. I'm checking if there's a nearby location close to my hit point where there is a irradiance value, and I borrow it, and then I store it. If not, and I have to do the calculation. But this isn't really the forward ray tracing algorithm that we motivated at the beginning of the lecture. So a different technique known as photon mapping actually does forward ray tracing in exactly the way you might think of. So in photon mapping, rendering happens in 2 passes. What that means is that we're going to do a bunch of computations that don't directly affect any one pixel's value, and then we're going to go back, make a pass of our pixels, and do our rendering. So in photon mapping, we have a pre-processing step where we cast a bunch of rays out from the light source, let them ping pong around in our scene for a few bounces, and just store them wherever they land in our 3D scene. So we might like bounce it 3 times, each time keep track of the decay of the light as it bounced, thanks to the BRDF and the cosine term, and then just attach it to some 3D location where it landed after some number of bounces. Probably not too many, because each time the amount of light decays quite a bit. So what do you end up with? Well, you end up with a 3D scene with a bunch of little points attached to it that we often call photons in photon mapping, which is basically a location in 3D space plus the remaining light power and the incoming direction of that bouncing ray of light. Now, let's think for a minute, what's the difference between photon mapping and irradiance caching? Would be a great exam question. So in photon mapping, the photons are leaving the light source in this initial pass before I do my rendering, right? So the yellow points that we see here in photon mapping all started at the light bulb and bounced outward. In irradiance caching, the irradiance values are gotten still from the backward ray tracing algorithm, just from different pixels. So the source is another pixel rather than the light source. Different way of putting it is that irradiance caching is still using the backward ray tracing technique, whereas photon mapping is using forward ray tracing. Now, just like irradiance caching, we need some efficient data structure for actually storing this number of photons. Here we're only showing like 30, but typically you have a ton. And so you need to be able to check really, really quickly as I'm rendering, my ray from my eye hit this point. Is there a nearby photon in my photon map? And so the KD tree that we've already discussed is a pretty standard data structure for doing that. So in the initial step of photon mapping, we're doing forward ray tracing and then attaching these photons to different points in the scene. Then in a second step, or the second pass of photon mapping, we actually do our ray tracing. So now we cast our primary rays. Those are the rays from the eye out into the world. And now, rather than our previous techniques, to get our secondary rays, we're not going to do a Monte-Carlo integral over the hemisphere, but rather we're going to choose them very strategically to just be nearby photons, because those are the places where we have information about our light source. And so this is sort of a biased technique where now you're looking at points nearby where you know the lighting, and you're assuming that those are distributed in a fairly reasonable fashion. You can actually combine this with irradiance caching and other techniques. All these things can be added together because they all have different advantages and disadvantages. If you use rendering software, you might have seen the phrase final gather. And that's this final step of maybe one bounce and using the density approximation from the hit points and the photons. So here's what photon mapping looks like. Notice that here we see all the photons. And if you recall the irradiance cache image, notice that they look kind of evenly spaced. And this is actually with respect to the pixels of the rendered image, right? Like with respect to this two-dimensional grid down here. And that makes some sense because of how the irradiance caching algorithm goes, right? The irradiance caching algorithm is sending rays out from pixels and then caching where they end up, the global illumination value. In photon mapping, well, now all the photons are like leaving the light source and going into the world. So there's no reason why they should be distributed in a way that knows anything about your pixel grid. And indeed, you see that here. These look pretty random. Not completely random. So for example, if you want to capture this caustic here, notice that, well, photon mapping is probably a pretty effective technique for capturing caustics because, well, just with high probability, rays will leave this object, go through the sphere and get focused down here. And then here's the final gather result. Notice it looks smooth because it's smoothly interpolating all this data here. So those are our two big strategies. They could be mixed and matched in different ways, which are irradiance caching and photon mapping, which both can be used to tackle global illumination. There are many other techniques out there. So another global illumination problem is subsurface scattering, where light enters one point on a surface, wiggles around underneath, and then leaves at another point. This is important for skin, marble, milk, these sorts of translucent material. So you can see here, this is without, and this is with. Here you might need the BSSRDF, which is like the BRDF for subsurface scattering, which says not just the fraction of light that bounces off a surface, but also the fraction of light that came in here and goes out over there. This is a complicated function, but these are the sorts of things that people study. Here's another subsurface scattering effect. And you can see that essentially rendering with this is what causes your skin to look a lot softer than if it were made of a material that doesn't have subsurface scattering. Incidentally, one thing that I thought I would point out to you all is an interesting article that just appeared in Scientific American pretty recently. And this subsurface scattering discussion is one of many where people talk about, rendering skin. And implicitly, many of the examples in these rendering papers are not very racially diverse. And indeed, it's the case that a lot of rendering technology for hair, for skin, and other aspects of computer-generated humans really have focused on a particular look for the humans that they're rendering in terms of race and ethnic background. This article is a really interesting one that I'll try to post on our course site as well, which talks a little bit about the history, and I think is especially in this sort of 2020 moment, and a good one to read. I think we think of computer graphics as maybe, an engineering domain that's somehow immune to some of the discussions that we've had more broadly. But the reality is that even in the mathematical, technical aspects of computer graphics world, even if we're not intentionally creating, technology that's somehow discriminative, these same biases and ways of thinking can creep in onto the technical literature. So anyway, I'll forward a link to this paper. I just thought it was worth mentioning as a bit of an interesting discussion. When you read papers on subsurface scattering, hair rendering, and so on, oftentimes they talk a lot about rendering hair and skin, but they really mean blonde hair and white skin. And there's some really, if nothing else, very challenging topics for the future of how to make that machinery essentially equally effective for a diverse and broad set of characters, like what we hope to see in the future of animated films, movie effects, and so on. In any event, all of these algorithms are just the beginning. There's so many Monte-Carlo techniques that are out there for rendering. There's bidirectional path tracing. Maybe you kind of meet your paths in the middle. Metropolis light transport, my PhD advisor was involved in, so it's close to my heart. And even finite element methods where you actually take the rendering equation and try to solve it like an equation, which if you notice, none of our techniques today really did. So the first thing you have to do is write it down, like what is the matrix of this system and how do you solve it? And so radiosity, pre-computed radiance transfer, and so on are all algorithms that actually do that, which are just amazing feats of mathematics and engineering. But the reality is that, of course, Monte-Carlo integration has appeared all over the place, even in our ray tracing lectures just in 6837, right? We used it for motion, We used it for glossy materials. We used it for depth of field. We've used it for global illumination. We've used it for anti-aliasing. Essentially, anti-aliasing. The point here is that our solution to all of our problems in ray tracing has been more rays. And if you look back, they're not just more rays, they're more randomly generated rays. And the point here is that we're oftentimes really trying to compute some fancy integral over like a hemisphere, or over, for example, in motion blurs, the integral is over different positions of your moving objects and so on. And the way that we keep doing that is just by randomly sampling different positions of our billiard balls, for example, and averaging the result. That's really just a randomized algorithm for computing an integral. Now, the domains of integration that we've seen in our lectures are also all over the place. Everything from two-dimensional domains, half spheres, time, and so on. So, of course, one thing that we might do then, noticing this pattern that essentially integrals are everywhere in ray tracing and global illumination, is to just think about how to compute integrals really well and what sort of techniques we need to make these integrals as accurate as possible. In particular, so far, we've just kind of scattered rays every which way and kind of hoped that they lead us to interesting locations in a scene with the relevant colors. But maybe we can try and come up with techniques that direct our rays strategically, but at the same time don't bias the rendered result. We have to be careful that the mathematics are preserved. So here's a bit of motivation. So here we see some glossy reflection, and of course there's a lot of different noise artifacts, especially with one sampler per pixel. That's far too few. Increasing the number of samples per pixel really increases the quality of the image. But even with 256 samples per pixel, if you have a glossy enough material, it doesn't look so good. There's still some noise. And so essentially what's going on here is that we're using these randomly generated rays, right? We just keep randomly generating more colors. And there are a lot of different byproducts of that. I mean, one is that, of course, if we run our algorithm a second time, we'll get a slightly different rendered image. In fact, if we average those two together, we'll probably get a better one. But we can also talk about it just in terms of random variables. Hopefully, many of you have taken a probability course at this point in your MIT career, and you can ask exactly these kinds of questions. Like, if I generate 100 images by calling my ray tracing code with all this Monte-Carlo integration 100 times, what is going to be the noise or the covariance, the standard deviation of each pixel, is a totally reasonable question. And what you want is probably for the standard deviation to be small. That's what you want, right? Because in other words, your rendering is reproducible. You don't have a wild amount of variance in the pixel colors that you're getting. So in order to do that, really, all we're doing is computing integrals, and we're doing it with a particular randomized strategy. The reason we're doing that is that, rendering is a continuous problem, but computers are discrete. They only know how to do finite numbers of computation, so we have to discretize things. We rarely can compute analytical integrals, meaning that there's just some formula for the actual integral of our function dt. Now, if you might remember from intro calculus class, you probably covered many different what we would call deterministic techniques, where you take a bunch of points, you sample their values, and then maybe you approximate your function. So here we've approximated it with like linear chunks and then summed up all these areas, and what you would get is maybe the trapezoid rule. There are all these different rules for approximating integrals, and a reasonable question you might ask is, well, why don't we use these in rendering? Because instead, we use a different technique called Monte-Carlo integration, which I've already alluded to, which essentially randomly draws these points on the horizontal axis and then uses their averaging in order to approximate the integral. So first, let's add a little bit of detail to this Monte-Carlo formula. In particular, one thing that you can check is that one way to estimate the integral of a function f on a set S is to randomly draw a bunch of points xi in S with uniform probability, evaluate f at those points xi, and average the result, right? That's what this 1 over n is doing. And then we need to scale by the volume of S. Now, this is just a generic formula. It's to randomly draw points, evaluate the function of those points, average their value, and multiply it by the volume of the domain. And one thing that you can show is that as n gets bigger here, this approximation converges to the true value of the integral. But the real question from an algorithm's perspective is how fast, right? Because that's really what's determining the speed of our ray tracer. If n is 10, then maybe we're sending 10 rays per pixel. If n is 100, then we're sending 100 rays per pixel, and that's a lot more computation time. So unfortunately, in 6837, we won't get to prove it. But one thing that you can show is that the variance of this estimator kind of looks like 1 over n. So if you want to have the amount of error, you're going to need 4 times the amount of samples. Then that comes from the average error here being proportional to 1 over square root of n. This is true not just in rendering, but actually true just for any method that uses Monte-Carlo integration. So for example, if you want to compute pi using a technique like this, you could take a square, throw darts in the square, and check if those darts land in the disk, right? Just by checking if their norm is less than 1, and that probability is pi over 4, right? So I throw a bunch of darts, I compute the fraction of the darts inside of the circle, and I can use that to compute pi. And I encourage you to try this at home. It's kind of fun to play with. One thing that you'll see is, of course, the more darts that you throw, the better your estimate of pi gets. Now, when you demonstrate this, one thing you might do is run this experiment where I send 100 darts and I compute pi a bunch of times and try to figure out how accurate it is. Like if I do it more than one time, how wiggly is this estimate about the true value of pi? And this is where the really key advantage of Monte-Carlo integration comes in for ray tracing. And that is that ray tracing is a huge high dimensional problem. In that sense, it actually has a lot in common with graphical models and some probability computations you do in machine learning and statistics. But the basic point here is that we're computing an integral over a giant space. And this convergence result about Monte-Carlo integration which tells you the variance kind of looks like 1 over n. Notice that the dimension of my integral is actually not there. Whereas if you look at the convergence of, for example, Simpson's rule, trapezoid rule, and so on, the number of samples that you need to increase the quality by a constant factor actually exponentiates in the dimension of your integral. Meaning that if you have to integrate over a high dimensional space, you need a ton of samples for these deterministic integration techniques to give you a more reliable value. So the kind of cool thing about Monte-Carlo integration is, it's not very efficient for computing pi because that is just some two-dimensional problem. But as I increase the dimensions of my integral, the nice thing about Monte-Carlo integration is that the time complexity doesn't scale in the number of dimensions, which is what's allowing us, for example, to do crazy things like that path tracing algorithm, which is really integrating over the product of a ton of hemispheres. Whereas deterministic methods that compute a grid of samples and then average the result actually get way worse as the dimension increases. And so that's the advantage. Moreover, there's fewer restrictions. It's pretty easy to integrate over hemispheres, cubes, intervals, whatever, using more or less the same result. But really, the key idea here is that Monte-Carlo integration extends to high-dimensional problems with the same level of crappiness that it has in low-dimensional problems, which is different than Simpson's rule, trapezoid rule, midpoint rule, all that stuff, which get exponentially worse as the dimension increases. And this is basically coupled with the fact that rendering is, and the, solving this rendering equation has integral over the product of a ton of hemispheres, so it is high dimensional. Especially when you are also accounting for anti-aliasing, soft shadows, all these other effects. Now, of course, there are disadvantages as well, right? I mean, can create noisy images like what we saw. The convergence isn't great, and implementing these things are pretty tricky. And so in rendering, there are a lot of different techniques out there that try to improve over the basic Monte Carlo integration that we have already introduced in this course. And essentially what they try to do is to bias your rendering in a different way. So for example, if I'm doing, rendering and there's a lot of detail over here and not so much over there, then maybe I want to kind of bias the rays that I bounce off of a surface toward the place where there's interesting detail that I need to account for. And these ideas go back to the 90s and even earlier, where essentially, rather than using these uniform samples like what we've talked about so far in lecture, right, this naive sampling strategy, we can use, I probably wouldn't say optimal, I would say like better strategies that try to focus our random samples in places where we think we're going to get interesting contributions to the integral. So here's a schematic of what that looks like. This is called importance sampling, is the keyword or phrase here. The idea is that if I have a function like the one I'm showing you here, by the way, our functions tend to be positive or non-negative in rendering, then the interesting contribution is really happening on the left-hand side, right? And for example, if there's a dip over here, I would like to see it because that's going to actually affect the color of my pixel. Here, there's not very much interesting going on. There's just very little light. So there's no reason for me to cast a bunch of rays in the direction where I'm not receiving a whole lot of light because the contribution to my integral is going to be really small. And so what do? I actually use unevenly spaced integration samples that bias the sample toward the left-hand side. But then when I compute my integral, I have to be a little bit careful to account for the spacing of the samples that I just did. So here's another example, which is glossy reflection. So in glossy reflection, you have a BRDF, which has like a giant lobe here. So if I'm doing my path tracing algorithm, would it really make sense for me to just uniformly distribute rays on that entire hemisphere? Well, the answer is obviously no, because if I randomly draw a ray in this direction, it's basically going to get multiplied by some tiny value, epsilon, that isn't going to contribute to the final rendered color a whole lot, right? And that's just by virtue of the BRDF being small. Whereas if I draw a sample in this direction, it has the likelihood of actually contributing a substantial amount of color. And so a typical thing to do is not to randomly sample this hemisphere uniformly, but rather to concentrate the samples in areas where the BRDF is high. And here you can see the result. So here we do a uniform sample of rendering this vase sitting in, I don't know, on a beach apparently. And here we do a biased sample, where the biased sample is trying to compute more samples in the direction of the lobe of the BRDF. And one thing that you can see is that you get a smooth, or at least smoother, rendered image as a result. And that's because the stochasticity of, did I randomly happen to draw a ray in the direction that matters for rendering? Well, now that's much more likely. And as we increase the number of samples, the difference becomes even clearer. So you can see that both images do get better, but on the top, it's still quite noisy, whereas with 25 samples per pixel in the biased case on the bottom, you have almost a smooth rendered image at this point. Or here's with 75. Okay. It turns out that if you want to do importance sampling, it's actually quite easy to account for that in your Monte Carlo integration formula. Essentially, you just need to divide or scale your sample by the likelihood that it is going to appear in your non-uniform distribution. The basic point here is that, if I'm trying to integrate some function and I have a ton of samples over here and then a few spaced out ones over there, well, the reason that I'm dividing by p is that there's a high probability of choosing samples on the left-hand side, which means that the spacing between the samples is going to be very small, right? So actually, high probabilities get a low weight because there's more values to be averaged together, whereas low probability regions, we need a high weight to account for the big space between the different samples. That's what's going on. The reality is, in practice, this is extremely simple to work with. If you bias your importance sampler, you just have to account for it in your Monte Carlo formula. So here's another example where if I use really nice importance sampling, I can get a nice smoothly rendered result. Notice that it's still not great from a computational perspective. They had to use 1,200 samples in every pixel to get it right. Now, there are many different variations of this strategy. For example, maybe you don't want your rendering to be completely uniform or uniformly random, but instead you kind of want a well-distributed set of rays. This is a bit different than the goal of biasing your sampler, but more just to make sure that you don't miss some part of your BDF more generically. One way to do that in stratified sampling is to kind of get halfway in between things like Simpson's rule and randomized Monte Carlo rendering. So here you can see the key idea, which is maybe if I'm doing my anti-aliasing, I do divide my pixel into a grid, but then inside of every grid cell, I kind of randomly perturb a little bit just to add that randomness. And this avoids clumping of your samples. Then, another term for this is jittering, which we already mentioned. Now, this is a cheap and effective way to make sure that you don't have high variance in your integrals. But if you do the theoretical analysis, sadly, in high-dimensional integration, that exponentiation, that curse of dimensionality creeps back in, and this technique becomes ineffective. So in very high-dimensional problems, Monte Carlo is pretty much the only choice. So anyway, this is an extremely high-level discussion, and the reality is that many people focus on this, but my goal here is just to give you some intuition for the considerations that go into these extremely high-end rendering algorithms with global illumination, where you're computing integrals of functions, which are themselves integrals of functions, and so on. It gets really complicated really fast. The basic point here is that, well, A, we use Monte Carlo strategies to replace these integrals with sums, and B, if you bias your Monte Carlo, sometimes you can make it converge a little bit faster as a function of the number of samples. And for every intuitive idea you might have for how you can make it converge faster, chances are there actually is a mathematical theory or algorithm out there that tries to implement it. And we've sort of outlined a few of the reasonable choices here. Notice for the most part in today's lecture, we've given you a bunch of Google search terms. These are advanced topics that will require an entire course. But it's mostly just to give you a flavor, and if you're excited about it, I would encourage you to explore it in your final project. So as a bit of a recap, we talked about the global illumination problem, we defined the rendering equation, and talked about why rendering really is some kind of a process of solving this equation in an extremely approximate fashion. We talked about different algorithms for solving global illumination, path tracing, irradiance caching, photon mapping, and so on. And then we spent a few minutes at the end of the lecture just talking about generic strategies for Monte Carlo integration, where essentially the idea is that you want to concentrate your samples where all the interesting action is. And you can do that at the cost of having to reweight your samples when you take that average. And finally, we talked about strategies like stratification that try to do something in between. Try to, on the one hand, have some randomness. On the other hand, make sure you don't miss stuff by confining your random samples to different grid cells, which can be effective for low to medium dimensional integration. This is a high-level discussion, and I really encourage you guys to dig into this stuff more. You can look at this physically based ray tracing book or many others, which go into tons of detail when it comes to global illumination and related effects. And it's a really fun topic to study. But with that, I think we're actually done with our discussion of ray tracing. And now our attention in 6837 is going to turn to high-speed rendering techniques intended for video games and real-time interaction. So with that, I'll see you next time.